Okay. So moving on with chapter 5. Okay, so I wanted to show you this video that we got forced to kind of skip last time. So this is a video that's sort of meant to illustrate hydrogen bonding for you in water, because that's one of the places where it affects our lives the most. And so it's meant to sort of drive home the point that these hydrogen bonds and all these intermolecular forces are very transient, they're very fast, they switch back and forth quickly, they're constantly moving around. And you can see all the little water molecules vibrating around, and you can see the hydrogen bonds kind of connecting them now at this point. And you can see they kind of flip around a little bit, they're not permanent. Zooms in for you. So this is how you want to think about hydrogen bonding. Now the hydrogen bonding are those little dotted lines, right? They're between two different water molecules that you're getting these bonds. So it's going to go ahead and rotate it around a little bit and show you what's happening. And freeze it for you so you can see them all sort of in a freeze frame. Okay, so that's sort of the idea of what's going on with hydrogen bonding. So things to sort of take home from this video. Remembering again that the hydrogen bonds are between two different molecules, they're intermolecular forces, and that they're quick. They switch back and forth, they aren't a permanent thing. And now we can move on. Okay, so covering this slide one more time since we did sort of rush through it at the end. So these were ion dipole forces. So this is very similar to a dipole-dipole force, only now it's not two different dipoles. Now you have a system where you have an ion and you have a dipole. Now that makes it so that the ion in the molecule that's polar can interact with each other, because you have this plus and minus side of the molecule, and it can interact with the plus or minus ion depending on which part of you're talking about. Okay? So if you have a positive ion, that's going to draw the negative ion toward it. If you have a negative ion, it's going to draw the positive side of the molecule toward it. And so you get these interactions between ionic compounds and polar molecules. So I mentioned this before, but again, this is one of the ways that you can sort of get salt to dissolve, is you can interact those sodium chlorides with water, because water is polar. And so when you're talking about this, you're usually talking about a mixture. You're talking about an ionic compound mixed in with a polar compound. Okay. So now we've sort of covered a lot of the stronger ones, and we need to move on and cover something called dispersion forces. So an example of this would be something like fluorine, F2. Now, is fluorine polar? No, right? It just has it has two things. They both happen to be electronegative, but they're equally electronegative. So it's not going to be polar. So why do I have dispersion forces drawn like this? Well, it's the same idea as a dipole-dipole force, except incredibly weak. The idea here is that if you have something like fluorine, it has some electron density around it, right? Now, most of the time it's going to be split 50-50. If you average all of it out, half of the fluorine is going to have half of the electron density at any given, any average point. But that doesn't mean that at any instant it does. Maybe some situation arises where one fluorine gets a little bit more of the electron density. Not because it's more electronegative, it's just a very quick, very transient setup where all of a sudden one fluorine ends up with a little bit more of the electron density. If it does that, what charge is it going to have? A little tiny, tiny, tiny bit of a negative. Not very much. It's not actively pulling that electron density toward it. It just happened to get some. But if it happens to be a little bit negative, what is it going to do to all the fluorines that are around it? It's going to kind of shove the electron density of the fluorine that's around it away a little bit. And so you get this sort of rippling effect because of it. And that's what we call dispersion forces. Now, everything has this, okay? Dispersion forces, everything that has electrons have it. So it's gonna be completely universal. Now, you can get stronger or weaker depending on the molecule, but everything has dispersion forces. So if I list a molecule and I say list all of the intermolecular forces that it would possess, dispersion forces is always going to be in there. These are also called London dispersion forces, so a lot of times it's shortened as LDFs, and that's fine. You can call them LDFs, you can call them dispersion forces, either way. The other way that they're often called is induced dipole. You'll hear that sometimes too, because what you have here is this isn't a real dipole. A fluorine isn't going to have a real dipole, but it'll have a little bit of an induced one for whatever reason. And so it'll induce, this induced dipole will induce a dipole in all the molecules around it. Okay? Now, these increases with increasing electrons. So what that means is the more electrons something has, the more dispersion forces it's going to have. Okay? So we talked about sort of comparing the strength of these when we talked about dipole-dipole too, right? We said if something has a stronger dipole, has more dipole-dipole forces. This system now, it's going to be based on how many electrons it has. Okay? Now let's think about that and see if it makes sense. So if something like, well, take fluorine. Fluorine has a lot of electrons, a few electrons, maybe compare it to bromine or iodine. Not very many, right? It's pretty small. So it has a pretty small cloud. So in general, you're not going to have a bunch of electrons. And with fluorine being way up at the top right-hand corner, is it going to hold its electrons close or just kind of let them a little bit looser? Close. Why? What term do we have there? Effective nuclear charge, right? It has a really high effective nuclear charge, so it's pulling all its electrons in pretty close. So I'd say that with something like fluorine with not very many electrons, it's something, we talked about this once before, polarizability, the amount that the electrons can move around, it's going to be pretty small. Now something like bromine or iodine, now that has a ton of electrons, and it's near the bottom of the periodic table. And so that means that it's not going to hold them quite as closely, and they're going to be able to move around a little bit more. And that ability of electrons to move around is called polarizability. So the more polarizability that something has, the more dispersion forces it has. To have more polarizability, you have to have more electrons. Now, if you go to explain this sort of thing to me on an exam, let's say, I say, tell me which one has greater dispersion forces and why. A lot of people will write down molar mass, which it turns out that technically that's true, that the higher the molecular mass, the higher the London dispersion forces, but that's not actually the reason behind it. The reason behind it is the number of electrons, okay? So you can think about it as increasing mass increases dispersion forces, but that's just sort of because how do you increase electrons without increasing mass? You can only do it so much, right? You can do it with ions, but can I add like 10, 12 electrons randomly without adding some mass in there somehow with like protons and neutrons? No. So make sure you realize that that's kind of your reasoning behind your London dispersion. It's all about electrons. If you put down molecular mass increases, so London dispersion forces increases, that's not right. That's not the reason behind it. Okay, so this was sort of what I explained to begin with. You have this one molecule that for whatever reason gets a little bit of a dipole. It's called an induced dipole. It's not real, it's not permanent, it's very temporary. And then all of the things around it end up with a little tiny bit of a dipole too. Little tiny bits, right? And it's not like when we were talking about dipole-dipole interactions where it was huge. Okay, so that's dispersion forces. So before we go on to a bunch of examples and a little bit of a summary again about everything that we've done, gecko feet. So, interesting aside, this is actually how geckos can stick to walls. Not all geckos can stick to walls. The leopard geckos that a lot of people have as pets, those don't have sticky feet. But the geckos that do, the way that it actually works is through these London dispersion forces and intermolecular forces. They have tiny, tiny little hairs on their feet, and all of that surface area, it turns out, will actually bond to whatever you stick it to. They have a hard time crawling up Teflon, but other things in general, they can just kind of climb their way up. And if you spend any time staring at geckos, they kind of look like they're double jointed. They aren't. What they actually do is they bend their foot backward and they can peel this off. So since these are intermolecular forces, they're not actually bonding themselves to a wall or anything like that. They can sort of peel themselves off and move their foot up, and peel themselves off and move their foot up. But as long as they aren't actively trying to do that, there's enough force here that they can just stick to whatever they walk on. So that's actually how geckos can climb. Okay, now I want to mention something called van der Waals forces. There's no real new information here, just what this term means and when you can and can't use it. So this is a term that you hear quite frequently, actually. Now, what this is it's an umbrella term for dipole-induced dipole, dipole-induced dipole and dispersion forces. Now, there's only one in there that we haven't talked about. Which one's that? This one, right? Dipole-induced dipole. Well, let's use what we already know to think about that. If you have a molecule with a dipole and it's mixed with something that doesn't have a dipole, it can actually induce a dipole, okay? So that would be another system where you have a mixture. You have one molecule with a dipole mixed with something that doesn't have a dipole, and so it forces one in there. In dispersion forces. So these are all classified under the term van der Waals forces. It's an umbrella term. It's a way to refer to all of them at once. It's also, you can sometimes just use it for an umbrella term for all intermolecular forces and just say any sort of intermolecular forces you have is a van der Waals force. It's a little bit, it kind of goes back and forth depending on which website and book you're looking at. Now, if I ask you which intermolecular forces are present in this molecule, I don't want you to use the term van der Waals forces. The reason why is it's not specific enough. It doesn't tell me that you actually know for sure which ones are there. I want you to use all the terms that we've just been talking about. Dipole-dipole, dispersion forces, ion dipole, hydrogen bonding, okay? Those are the type of terms I want you to use when answering questions, because with dispersion forces in here, everything has van der Waals forces, right? Some are just going to be stronger than others. So this is such a broadly used term that I don't want this for specific answers. I want all of the things that are basically headings on the other slides, and we'll summarize again here on this next slide, all right? But you should be aware of the term. You shouldn't ever hear that term and think, what is that? You definitely want to know what it is, because it's used a lot. It makes a handy umbrella term for everything. Okay. So let's go through kind of everything that we've talked about today and then the end of last class and summarize all of this up. Okay, so our strongest of the intermolecular forces that we've talked about is the hydrogen bonding. Now, remember the rules for this. You have to have a hydrogen that's bonded to a nitrogen, an oxygen, or a fluorine. But that specific bond, that's not the hydrogen bond, right? The hydrogen bond is between two different molecules. If I were to point to a molecule and say, draw the hydrogen bond, that would be a trick question. You'd have to draw another molecule next to it and then draw the hydrogen bond. The next one down is dipole-dipole. So these only occur in molecules that have a dipole. So anytime you see a molecule and I ask you what intermolecular forces are in there, you need to decide whether or not there's a dipole. If there's a dipole, then it has dipole-dipole forces. And then the last one being dispersion forces, and everything has dispersion forces. Within each one of these, you have a large amount of gradient, right? If something has a lot of hydrogen bond donors and acceptors, lots of places that it can hydrogen bond, it's going to have more hydrogen bond and it's going to be stronger. If you have something that has a very strong dipole, that's going to have more of these dipole-dipole forces. Everything here is a gradient. And with dispersion forces, remember, increases with amount of electrons. Okay. Now to actually do, yeah.
Does the dipole-induced dipole count as dipole-dipole?
The dipole-induced dipole isn't actually listed in here because it's sort of an in-between. It depends on how strong the dipole is, what other molecule you're talking about, so it's harder to rank as easily as it is here. Even these have a lot of crossover. We'll look at an example in a minute where I show you some dispersion forces that are actually higher than the dipole forces. So there's the amount of dipole, I should say. So there's a lot of kind of leeway there. Yeah, that was what she was just asking about. So that's a little bit harder. Oh, the ion dipole. Okay, actually it's the same idea. It sort of depends on the system, so it's a little bit harder exactly to rank. It's definitely, both of those are definitely going to be higher than the dispersion forces, probably just included in the dipole-dipole area for the sake of sort of working on it, but you can kind of think of them all in this area, but they all sort of depend, and they all have crossover. So use this list as a guideline, not an absolute, okay? There's definitely some places where that's not true, and I'm sure Sapling brings up a few of them, even though I can't remember them off the top of my head. Yeah. how strong a dipole is. So good question, especially reviewing for the exam thinking. So how do you know how strong a dipole is? Well, the stronger, the bigger the difference in the electronegativity between all of the systems that you're comparing, the higher the dipole is going to be. So if you have two things that have a little bit of a difference in electronegativity, but not very much, that's not going to create a very strong dipole. And then of course you also have to worry about whether things in a molecule with lots of atoms are canceling each other out or not. Okay, so since I know you've been missing them, we haven't seen them in a while, let's go back to this. So I'll give you a second to pull them all out. So now we're going to go through all of those Lewis structures that we've been going through. We're going to decide which ones have a dipole. Or excuse me, which molecular forces are present. We already did the dipole part. Okay. Sounds like you're still looking, so I'll give you a minute. All right, so the first one we have, N2. So we're listing all of the intermolecular forces that are present. So what do we have for N2? Do we have hydrogen bonding? No. Do we have dipole-dipole? No. Do we have dispersion forces? Yes. So just dispersion. Okay, so our next one. CH2O. So, do we have hydrogen bonding? And careful before you answer, give it a second glance. No, right? But we have hydrogens and we have oxygens, so why don't we have it? Awesome. They aren't directly bonded, right? You can't just have a hydrogen and an oxygen in the same molecule and have it be hydrogen bonding. You have to have the hydrogen and the oxygen actually bound to each other. So there's no hydrogen bonding. What about dipole-dipole? Yeah, because the molecule has what? It's polar, right? It has a dipole, it's a polar molecule, and so there's going to be dipole-dipole. And then what else? Dispersion, good. Okay. Our next one. Yeah, that one doesn't work as well for this one, so we're going to skip that one. There are some in here that don't necessarily apply overly well to everything. Okay. XCF4, 4+. So, what do we have here? Do we have hydrogen bonding? No. Do we have dipole-dipole? Okay, so let's back that one up a little bit then, since it seems almost a 50-50 split. Do we have polar bonds? Yeah, we definitely have polar bonds, right? We have XC, every one of these is polar. Is the molecule polar? No. Why? Well, we have this shape, right? Which is, what is this called again? Tetrahedral. This shape. And if I was holding these all perfect, what would happen to all of these? They would all cancel, right? So, if you have a hard time seeing that, sort of my way I like to kind of think about it, if you don't want to think about it in mass terms, is put a little person as the central atom and, connect things to them and have all of the outside atoms pulling on him. So let's look at this again. Let's look at a trigonal planar one though, because it's a little bit easier, maybe. So if we had something like this, and we put a little person as the central atom, and we put people on all sides of them pulling away from them, which way would the person go? Nowhere, right? Hopefully they're not pulling too hard and not hurting them, but basically they'd go nowhere. Well, let's look at like a bent molecule. If we had a person standing in the middle and we had someone pulling that way and someone pulling that way, which way would they go? Straight toward you guys, right? The side to side would cancel, assuming they're pulling with the same strength, and they would just go walk that way. Okay, so think about that, if it helps. So now going back to this example, we have XEF4. So all of the polar bonds are going to cancel each other out. So is there a dipole? No. So since there's no dipole, is there going to be dipole-dipole forces? No. So no hydrogen bonding, no dipole-dipole. What's left? Dispersion. And we haven't been talking about the ion dipole or anything like that here because we don't have a mixture, so there's nothing to really talk about until we have a mixture of compounds. Okay, next one. So we have this. Now, are we going to have hydrogen bonding? No. Are we going to have dipole-dipole? Does it have a dipole? Yeah, do we have any polar bonds? The nitrogen and the oxygen is. Sure, they're both electronegative, but it's still polar. And we have a charge which helps show you that too. We have a negative charge here and a positive charge here. So it'll have a dipole. So is it going to have dipole-dipole forces? Yeah. What else? Dispersion forces, right? So this is how you kind of go through and decide, well, what does everything have? And we're going to use this in a minute to actually try to decide on some melting points and some boiling point rankings. All right, what does SF6 have? Does it have hydrogen bonding? Does it have dipole? Does it have dispersion forces? So that only has dispersion. Okay, next one. XCF4 without the 4+. No 4+ this time. Now, do we have hydrogen bonding? No. Do we have a dipole? I heard a few yeses, and then everyone jumped in with no, but let's do it anyways. So what shape do we have? Let's go electron geometry first. What electron geometry do we have? We have octahedral, right? So that's like 6 sticks. Now, we remove the first one, the first atom, to put a lone pair there, and it doesn't really matter where we take it from, right? They're all the same. When we remove the second one to put a lone pair, do we take from one of the sides or the top? Top. So make sure you can do this without the Lewis structure sitting in front of you too, right? Because I kind of have the Lewis structure drawn to show you the geometry, but make sure you realize I could draw the Lewis structure to trick you. Sapling does it all the time. Okay, so what shape is this then? Square planar. So now, do we have polar bonds? Yeah, all of them. Now, is the molecule polar? No, right? They all cancel. This and this cancel directly, and this cancel directly. So, do we have dipole-dipole forces? No. So, what do we have? What's the only thing we have? Dispersion, which I'm going to call LDFs now for a while, just to get used to seeing it both ways. So you can write either one. LDFs is shorter, which makes it nice. All right. BH3. What do we think? What type of forces do we have here? Do we have hydrogen bonding? No, right? It's not bonded to an N or an F N, O, or an F. So we don't. Dipole, dipole? No. Well, if it was like a nitrogen in here, if it was a nitrogen in here and it had a lone pair, then it would be. Then you could hydrogen bond it. Ammonia will hydrogen bond. Is that what you were asking? Oh, well, if the nitrogen was in here, then the nitrogen would be directly bonded to the hydrogen here, and the hydrogen here, and the hydrogen here. So then it would be, yep. Yeah, it can, the nitrogen and the hydrogen can be bonded to a few different things. That's fine. Is that where the confusion was, maybe? Okay. Okay, so now in this case, do we have any dipole? No, right? You may or may not know whether those bonds are polar. Honestly, it's a little bit on the close side, but even, you don't have to know that. Why? Yeah, even if they aren't polar, well, then you don't have to worry about it. If they are polar, well, they all cancel out, so you don't have to worry about it. It's between two molecules, but to have it, I need something to write down. But in order to have it, you have to have a directly bonded hydrogen to an oxygen, nitrogen, or a fluorine. Because what happens there is the difference in electronegativity makes it so that that hydrogen bonding can occur. It gives it sort of this little area where there's this dipole between the oxygen and the hydrogen, or the oxygen and the the hydrogen and the nitrogen, or the hydrogen and the fluorine. And so what happens is in that area you get that delta positive and the delta negative that can do the hydrogen bonding. Yeah. Exactly. So I'm going to repeat what she just said because it's perfect. What she had asked / asking me to confirm is that within one molecule you have to have a hydrogen bonded to an O, an F, or an N, but then that molecule is going to be hydrogen bonded to a different molecule which also has a hydrogen bonded to an O, F, or an N. Yeah. It would be. It would be hydrogen bonded to another molecule. I mean, technically, if I was going to draw it, I'd have to draw that other molecule, but it would be. Anything else? So I should repeat what she said because you guys probably couldn't hear it. She had asked if it was an N in the middle. What would it be hydrogen bonded? And it would be, right? If it was an N instead of a B, it would be. Now, the difference there is that it would have a lone pair, so your geometry would move around a little bit, but it would be hydrogen bonded. Okay. All right, this one I want to talk about only to tell you why I wouldn't actually require you to be able to do it. So I skipped this one when we did dipole because I thought it was a little bit hard. But since it ended up showing up on your discussion worksheet in similar form, I want to talk about this one just a minute to say something like this. I wouldn't ask you on an exam about a dipole there too much. The reason being is that all of these bonds are polar, but they're polar with slightly different values, right? Because you have an oxygen here, which is more electronegative, but then you have these 3 chlorines, and it would be really, really hard to tell whether they cancel or not. You could do it. You could figure out, you could go to a table and you could calculate them all out, and you could figure out the differences, and you could add the bond vectors together. That's definitely doable, but I'll let you take a vote. Do you want to do that? All right, well, then we won't do it, since you asked. So I put that one up only for the sake of letting you know that something like that you wouldn't be required to tell me on an exam. All right, ClF4 minus. What do we think about this one? What intermolecular forces does this have? So first one, do we have hydrogen bonding? No. Do we have a dipole? No. Do we have polar bonds? Yeah, but it's not polar, right? They all cancel out. So when you look at these, all of them cancel out. They're square planar. So if you're not sure about that, go home and do what we did before with the other square planar one and make it and see what happens. So what's the only force we have to worry about, or intermolecular force we have to worry about here? Dispersion. or LDFs, whichever you prefer to call it. All right, this one. So this is our resonance structure. So what do we have to worry about here? Hydrogen bonding? No. Dipole? All right, we'll do this real quickly. Dipole? No, right? Just because it has polar bonds, they all cancel. So even though it has polar bonds, it's still not going to have a dipole. So what do we have to worry about then? Dispersion. So LDFs. Okay, and that's our last one. Oh, actually, it's not quite our last one. It's just our last one that we did in actual class. So let's look at HCO2 minus, which that was one that was on the video, right? Because I ran out of time a little bit. So what about the HCO2? What do we have to worry about there? Hydrogen bonding? No, it has a hydrogen, but it's not bonded to the oxygen, nitrogen, or carbon. What else? Dipole, dipole? Yeah, dipole, dipole, right? Because it's going to be split halfway between here and here. And then what else? LDFs. You always have to write LDFs. Okay, so remember that one you have the notes on. It's from your video. It's just, we haven't been doing it in class quite as much as the other ones. Okay. So that sort of walks you through how to go through and identify them all. Okay, now let's actually use all of these for something. And we sort of have alluded to this in the past, but we haven't actually got a chance to really talk about it in detail. Effects on boiling point and melting point. So first, let's think about what's going on when you boil or melt something. And what the intermolecular forces, let's just go ahead and assume it has something to do with intermolecular forces here, right? Since we're talking about intermolecular forces. What's going to happen if those increase or decrease? So first of all, think about what's going to happen. If you have something boiling, what are you really doing? Are you breaking the bonds within a molecule or between molecules? Between them, right? You're taking like two molecules that were just kind of like hanging out, rubbing around, and then flying them off into, wherever. Now with melting, you're taking and you're saying, well, you have all these nice molecules in a packed lattice, and then you're letting them kind of flow in between each other now, okay? In both cases, you're breaking the intermolecular forces. You're taking the forces between the bonds, and you're keeping them from either holding them in these rigid little structures, like for instance, you can kind of think of it like the classroom, right? You're all sat in these little chairs, and you can't really move too much. And then we let them melt. That would be like, releasing the class. But you're all kind of, if I had you all stay in the aisles, you'd all still be touching. And then boiling would be sending you off into the world, right? Where you can all spread out and never talk to each other again until you come to class again. So now, what happens if we change these intermolecular forces around? So now we increase the intermolecular forces. We take the two molecules that were being held together, like this, and we increase those intermolecular forces. Is that going to make you have to put more heat in to break the bonds or less heat? More, right? You increase the forces, so you increase the amount of heat you have to put in. So does that raise the boiling point or lower it? Raises it. Good. So just to say that one more time, if you have a compound and you have more intermolecular forces, you're going to have a higher or lower melting point? Higher. More intermolecular forces would equal a higher melting point or a higher boiling point. Less intermolecular forces is going to equal a lower melting point or a lower boiling point. Okay? So now we can take all the things that we just learned about intermolecular forces and just directly apply them to melting point and boiling point. So there's sort of a few, this is a graph that comes from the old book, but it's quite useful. So notice what's kind of going on with each of these lines. So this is H2O, H2S, H2SE, and H2TE. So that's basically your hydrogens bonded to oxygen and then the group going below it, right? These are hydrogens bonded to fluorine and then the group below it. nitrogen and then the whole group below it, carbon and the whole group below it. Now, if you look at these, you notice what happens between here and here. You have this giant drop. Why do you have this drop between water and sulfur in boiling point? What does water have? That's hydrogen bonding, because H2S doesn't have hydrogen bonding, right? And the same thing here. You have hydrogen bonding for HF, but not for HCl. You have hydrogen bonding for NH3, but not for pH3. And so you get this giant drop, okay? Why don't you have it here? Carbon doesn't have any hydrogen bonding. So for this, you get this steady increase. What is this steady increase due to then? What kind of intermolecular force? Dispersion forces. It's more, you're going down a group, and we're going to look at one of these in a little bit more detail, because you can make some arguments for whether one of these is, right or wrong. As you're going down a group, you're adding entire shells of electrons. You're adding lots and lots of dispersion forces. And so the more dispersion forces you have, at this point, starts making the boiling point increase. Okay? Okay, let's do a bunch of examples. So we're going to go through and do all of these. I've changed a couple of them around. We'll get to as we go through. All right, so first let's rank argon, helium, neon, and xenon. So if we want to rank these in order of boiling points, or melting points, we really only have to talk about one thing, and that's intermolecular forces. So by ranking these according to boiling point or melting point, we're also ranking them according to intermolecular forces. So what is the only intermolecular force that we're dealing with here? Dispersion forces, right? They're the noble gases. They don't have anything else going on. They can't have a dipole, there's only one atom. They can't have hydrogen bonding, there's only one atom. So only dispersion forces. Now, why would dispersion forces increase? Number of electrons, good. Not molecular mass, number of electrons, which happens to go hand in hand. The number of electrons is the reasoning. And why? What happens when you increase the number of electrons? What's the key word here? What goes up? Polarizability, right? The amount that you can move the electrons around goes up. Okay, so let's rank these. So what one would be our lowest then? Helium. And then we would just go down the periodic table. Now, it makes a lot less sense to talk about the noble gases here, because what do we also know about these? They're all pretty much gases, right? And they have hardly any intermolecular forces at all. And so they're pretty much always all gases, but you could still go through and do it. Okay. Now let's pick a significantly more complicated example that's still doable. This one. So now we have to figure out what sort of intermolecular forces we have going on. So what do we have in nitrogen? Just dispersion. What about CH4? Just dispersion. Now, what about pH3? Well, let's draw it out. If you draw it out, you're going to have this shape. So what electron geometry is that? Tetrahedral. What molecular geometry? Trigonopyramidal. Does it have a dipole? Yeah. Which direction would it be according to how I kind of have it drawn? Yeah, down like the middle of all the hydrogens, right? Okay, so what sort of intermolecular forces does it have? And what else? Dispersion. Now, what does water have? Yeah, it has H bonding, it has dipole-dipole, and LDFs. So it has everything. So I'm going to read those off because it's not the easiest thing to see. Sorry about that. Dipole, dipole, and dispersion. Just dispersion. Just dispersion. hydrogen bonding, dipole, dipole, and dispersion. Okay, so that's all of them. Okay, so now we have to rank these. So which one kind of right off the bat can we say is going to be the highest? H2O. Right? Has hydrogen bonding, it has a dipole, it's going to definitely be the highest in this case. Now, what two do we think are, or what one would you say next? Yeah. Okay, and then which one? That one's tricky, right? Now we have just two dispersion forces. So we have CH4 and we have N2. So which one do we think is going to, how are we going to decide? Yeah, so as far as you guys are concerned, we can just go with number of electrons. So, yeah.
Can you explain the dipole-dipole for the H3 again?
Yeah, so you decide if something has dipole-dipole forces, you just decide if it's going to have a dipole. And so if you look at pH3, you have 3 bonds that are a little bit polar. Not by a lot, but a little bit, going in those directions. So all the side-to-side part cancels. And then what direction would the dipole be if I'm holding it like this? Straight down the middle, right? Because they would all add down the middle. Okay. So how are we going to decide between nitrogen and methane? Number of electrons. So if you count up the number of electrons, nitrogen has less. And so you have that. Okay. That's the level of difficulty I'd expect from you on an exam. All right? I won't throw anything more difficult at you than that. Which I recognize right now that might not seem easy, but there are much harder ones that get thrown at you in various places, and that I won't do. Okay. Next one then. The next one is just some sort of discussion problems. So I'll flip back over to the laptop for now and just move over if I need to. Oh, hang on. Sorry, I see you all writing. You don't need to write this, that's on your notes. Okay. All right, so now moving back to the slides since it's mostly discussion problems. So why would bromine have a lower melting point than sodium bromide? We haven't really talked about ionic bonds in here. Now, what do we know about ionic bonds? We know that they actually are between different atoms, right? We talk about them as being an ionic compound, but they're between the different atoms. So those are really, really strong. They're kind of like, you could almost think of them as a dipole-dipole force taken to the absolute extreme, right? Now they're such a strong dipole, you have a plus and a minus. There are 2 ions interacting. So something like sodium bromide, that's an ionic compound. That's going to have a really, really high melting point or boiling point, because you have this massive, you have this ion here and this ion here. Your ionic compounds are always going to have a really high melting point because of that. Now, what about something like this? We have C2H5OH. So you would want to make sure you can draw that, right? What do we know looking at this that we have? What intermolecular force? Hydrogen bonding, right? We have that OH right here. It's because of this OH group. Now we look at this, do we have hydrogen bonding in that group? No. So why would that have a higher boiling point? Hydrogen bonding. Now water has a higher boiling point than H2TE. Why? Hydrogen bonding. Acetic acid has a lower boiling point than benzoic acid. So this is acetic acid, and that's benzene. So why would benzene? Yeah. So they both have hydrogen bonding. This one's actually a little hard. I could ask you to explain this one. I couldn't actually, probably in fairness, I could, I won't though. I wouldn't actually ask you to figure this one out on your own. I would ask you to explain it. But yeah, it's because you have more electrons, okay? So because you have more electrons, you have more what? Yeah, there's some other things going on there too that you'll learn about next year, but we'll leave that alone for now. Okay. So the benzoic acid does, because you have all of these carbons and all of the hydrogens that are a part of that. Okay. So we've already been over that, and I'm going to skip it for the sake of doing these. All right, let's look at some more examples. Put in order of increasing boiling point. So we'll do these on the document camera, so I have them written down for you. All right, so put them in order of increasing boiling point. So we have to look at what sort of forces we have going on here. So we have CH3F. What forces do those have? Yeah, dipole, dipole. In dispersion. And what about this one? H bonding. Dispersion. And then dipole, dipole as well. And then this one. Okay. So now we can rank all of these. Now, we have a bit of decision making to do. Which one's going to be our highest? Let's get that one out of the way. Yeah, this one. So that one's definitely going to be our highest. We'll just get that one out of the way. Now we have some more. This is not supposed to be H3F. This is supposed to be H4. Sorry. I changed it because it was too hard the other way. That should be H4. Say that one more time. Yes, dispersion as well. And hydrogen bonding. Okay, so we have all of those. Sorry, I got thrown by the fact that it was a much harder question than I meant it to be, and it was just, that didn't get changed. So that should be CH4. Okay, so what comes after this? NH3. Now, why is NH3 lower than this? Good. You can rank them in order of how many places there are that you can have hydrogen bonding. So the reason that you can rank this higher is you have two. It has hydrogen bonding that, and again, remember it's between different molecules. But another molecule could come and hydrogen bond to this area, and another molecule could come and hydrogen bond to that area. Okay? So you have this sort of system set up where you can have multiple types of hydrogen bonding going on. And then the last one is CH4. Okay? Now our last ranking question. We have propanol, dodecane, and propane. So I'm going to switch over to the laptop where I have them drawn for you already. So we have these. So we have propanol, dodecane, and propane. If I were to ask you these, I would draw them out, or I would give you the formulas, one of the two. So which one do we think is going to be our highest? So you think propanol, right? And then which one do you think? And then? Okay, that's really good logic. It's not quite right though. So, well, how it really ends up going is I'm actually going to write out the boiling points for you. And I want to explain this because it shows up in lots of places, and it's worth noting that it happens. Those are actually your boiling points. Now, so the propanol is your highest because you have your alcohol group there. And then your dodecane is, or excuse me, if it was the same size. Why is dodecane higher? Dispersion forces. But I thought that hydrogen bonding was stronger than dispersion forces. Good. So you guys have the right idea, so I'll explain it for everyone else now. So there are times where there's exceptions, right? I told you that those rankings were kindas. You can compare things that are similar size using those rankings. But when you start getting into situations like what we have on this screen, you can't compare them just using those rankings. Dodecane is huge. you have tons and tons of electrons. And so even though there's no hydrogen bonding and no dipole, it has that boiling point of 218 degrees. And so keep that in mind, that you can actually have exceptions to this, and it shows up.